So I'm happy to introduce Andrew Geiss. We'll be talking about deep learning for radar filling, infilling, and super resolution.
All right. Yeah, so this is a project I've been working on with Joe Harden at PNNL. So some background, kind of the overall purpose of this project is to explore applications of machine learning to radar data quality issues. And it's one of the projects funded by ARM under their machine learning investments. So yeah, in this talk, I'll be talking about a couple applications of deep convolutional neural networks. One is to doing radar super resolution, and the other is to doing radar blind zone mitigation. So first I'll talk about the super resolution. So the idea here, I guess you just heard a little bit about super resolution in the last talk. The idea is basically, can we use a convolutional neural network to artificially enhance the resolution of radar data? And the motivations for doing this are, there's quite a few. So some possible motivations are to try to combat the range velocity resolution trade-off in Doppler radars, to do non-uniform beam filling, so combat the fact that the radar resolution drops off with distance from the radar, just to produce nicer looking broadcast meteorology products, and to potentially do transfer learning between radars where we train a neural network on a higher resolution radar and try to apply it to one that operates at lower resolution. So the setup to tackle this problem is we're going to train a neural network by taking radar data and artificially degrading it, and then training the neural network to restore the original data. And the data I used to do this was all taken from the Langley Hill radar that sits on the coast of Washington. So for both of the problems I'll talk about today, we're using what's called a UNet style neural network. And this is just a diagram of the network in the center of the slide here. Each of these circles corresponds to several convolutional layers. And the idea is it takes some input over on the left, and it has this downsampling branch. Each of the downward pointing arrows involves doing spatial downsampling, and then an upsampling branch on the other side. And then there's some skip connections that go across between like resolutions that include some additional convolutional layers within those skip connections. And the reason to use this neural network is this network architecture was originally developed to do image segmentation, and the idea is they're particularly good at combining large-scale context information with small-scale pixel level and texture information. And we've actually been doing some experimentation with this recently, where we're modifying the neural network itself to force it to strictly enforce conservation laws. So this is a way to enforce conservation laws that doesn't involve modification of a loss function. It involves modification of the neural network. So these are some examples of the super resolution. This is showing NextRad or reflectivity from that NextRad radar. And I just have two examples on this slide. There's 4 panels each. So I have an example of doing 4 times super resolution and 8 times super resolution. And each of these, the ground truth is the upper left plot. And then next to it, I'm showing the degraded data. That's the input to the neural network. In the bottom row, I show the output from the neural network and the result of doing bicubic interpolation, which we're using as sort of a benchmark here. And you can see just qualitatively looking at these examples, the neural network is pretty significantly outperforming the bicubic interpolation in terms of producing high quality output. So for the 4x case, you can see here the neural network does a very good job of kind of preserving these tendril-like structures in the precipitation data when compared to the bicubic interpolation scheme. So here's some quantitative analysis of the performance of the neural network. In the table on the top, I'm showing mean absolute error, so pixel level mean absolute error in terms of reflectivity. And you can see the CNN over on the right here. So smaller numbers are better. The CNN is doing quite a bit better than these other schemes. These 4 other columns are all interpolation schemes that we're comparing to. And then we also use these 2 metrics to try to assess the perceptual quality of the output. So this is on the right here, I'm showing structural similarity index. This is typically used in computer vision and image processing. It's a dimensionless metric. Basically, higher values are better, and they kind of it expresses the the perceptual quality when comparing two images together. So basically, yeah, the CNN, this box is showing values computed over a test set, and the CNN does quite a bit better than these interpolation schemes. And then we also look at the spatial power spectral density of the outputs. So in this plot on the left, the blue curve is the original high resolution data. The green curve is the output from the neural network, and the other three curves are the output from interpolation schemes. And the idea is you would like to be as close to that blue line as possible. So the other application that I wanted to talk about was using convolutional neural networks to handle beam blockage and radar blind zones. So the idea here is to see if a neural network can basically fill in missing data regions in radar data. And the motivations to do this are, it's just a way to handle instrument failures and low-level blind zones and beam blockage, which are common issues with radars. One of the potential applications of this is we're working with ARM radar data to do this. So we could potentially develop a radar data set where all of these features have been in-painted with plausible looking data, so that if you're doing a research task and would like to do some high-level processing of the data like feature detection and tracking, you don't need to worry about doing a bunch of pre-processing and error handling first. And then again, there's another potential application here of doing transfer learning between radars. So training this on one radar that doesn't have a blockage and then applying the neural network to another one that does. So yeah, the setup's very similar. We're going to take good radar data and intentionally degrade it, and then ask a neural network degrade it by just removing a big chunk of it, and then ask a neural network to try to fill in what we've taken out. And the data we're using here is all radar data that was collected as part of the ARM cacti field campaign. It comes from a KaZR vertically pointing Ka-band radar and a CSAPR scanning radar. So this is my first example here. This is KaZR data. So this is a time versus altitude plot of reflectivity. The reflectivities are just normalized in this plot, so they're dimensionless. So yeah, the idea here is what I've done is kind of simulated a failure for a small chunk of time, and basically taken all of this data in this big missing region out, and asked the neural network to try to reproduce the ground truth, which is shown over on the left, or sorry, shown over on the right. And this is the results. So here I've trained this neural network just to optimize on the L1 loss, or mean absolute pixel-wise error. So it qualitatively does a reasonably good job at reproducing kind of the large scale structures that we're missing, though the result is kind of blurry. Here's another potential application. Again, here I'm showing data from KaZR. And in this case, I'm including other fields. So I'm including Doppler velocity and spectral width fields in this process. And the idea here is to simulate a low-level blind zone. So I've taken out a bunch of this data in this region labeled missing here, and asked the neural network to reproduce what was there. And the ground truth is shown down on the bottom. So this is what the neural network comes up with. And yeah, it does a reasonably good job of taking these kind of diagonal structures and continuing them down diagonally into the blind zone region. So here's some quantitative results. At the top, I'm showing just the mean absolute pixel-wise error for the in-painting time period in the KaZR data. I compared it to just conventional in-painting schemes that are, I'm not going to talk about them much, but examples of them are shown up on the upper right there. And yeah, in terms of pixel-wise error, the convolutional neural network pretty far outperforms those infilling schemes. On the bottom, I'm showing results for this low-level blind zone in-painting. And the idea here is I'm actually showing errors where I've used blind zones of different sizes. So the vertical axis is the vertical extent of the blind zone. The horizontal axis is the error. Lower errors are better. So the curve being farther to the left is better. And the convolutional neural network, the blue line, tends to outperform our baseline, which in this case is just repeating data at that lowest level down to the ground. And interestingly, the CNN does even better as the blind zone gets bigger and bigger. And then the last example I have here is an example using the scanning C-band radar. So the idea here is to simulate a beam blockage. So this is pretty common where a radar beam will be blocked by terrain or nearby objects. And here what we're doing is I'm actually applying the convolutional neural network in the radar sort of native coordinates and polar coordinates, and then I'm just plotting the results in the Cartesian coordinates. So what that looks like here is there's this big missing chunk that I've taken out that's sort of a wedge simulating a pretty large beam blockage right next to the radar. And then I've asked the neural network to try to fill it in. And this is the result. And again, I'm comparing to I'm showing mean absolute pixel-wise error here, comparing the convolutional neural network to two conventional in-painting schemes, and it does quite a bit better. And then lastly, I just wanted to show a couple examples. You heard a bit about conditional generative adversarial networks in the last talk. So I wanted to show a couple examples where I'm trying to use those to solve this in-painting problem, where we're basically using a combination of the pixel level, mean absolute error, and this sort of adversarial loss that is kind of like an estimate of the realism of the output. So this is similar to the very first in-painting example I've showed. This is KaZR normalized reflectivity data. It's time versus altitude plots. And again, what I've done here is taken this data that's shown on the left, that's good data, and basically removed this huge chunk of data right in the middle, and asked the neural network to try to reproduce what was there. So the output from the adversarial network is shown in the middle. And you can see here, there's maybe a little bit of artifacting. You can maybe tell that there's something strange going on, but it's actually done a very good job of reproducing realistic small-scale structures in that region that it's in-painted. It's of course not quite a bit of the information is lost when I remove this data, so it's not actually what was there in the ground truth, but it's at least realistic looking, small-scale variability. And then just for reference on the far right, I'm showing the output from the neural network that was optimized just using mean absolute pixel error. And so up in the upper right here, I'm showing mean absolute pixel errors for these various techniques, the GANs on the far left, and that actually, performs worse by this metric than the other methods. But there are, certainly applications where you might be more interested in producing realistic, turbulence or small scale variability than you are in optimizing pixel level errors. And then my last example is showing basically applying the same method with data from the CSAPR. So the top row is showing ground truth data, and the bottom row, this is the exact same example that I showed earlier. So the bottom row, I've blocked out this a very large wedge kind of on the left side of the scan. And yeah, basically the generative adversarial network does a fairly good job of filling this in with something that looks very plausible. You can see maybe there's a little bit of artifacting going on, but it's come up with something that contains the sort of small scale variability you would typically see in this radar data. So that's it. So just a quick summary of the, neural networks do a pretty good job of enhancing and repairing radar data, and they typically can give a 5 to 10% improvement in terms of pixel-wise error metrics, and they do substantially better when you look at various metrics that evaluate perceptual quality of the output. And then, yeah, lastly, we can use adversarial learning to try to reproduce or create realistic small-scale variability in these outputs. And then our ongoing work is, like I mentioned earlier, we've developed a method to enforce conservation laws under 2D averaging for this super resolution task. And then we're also interested in trying to apply these adversarially trained networks to just doing detection of poor data quality periods.
Great, thanks. So I'll jump right into the questions we can get through for you. I'll ask two pretty short ones since I already know the answer, and then Chandra, I think, was going to ask one. So Manish was basically wondering if you'd tried to predict 3 together rather than 3 individually.
Yes. So for the the cases where I was showing 3 fields, those are all inputs to the neural network, and it's trying to predict them all at the same time.
And then Shanglin was asking if you'd tried applications listed things like unfolding radial velocity.
Well, yeah, so I've been working on some code to do unfolding of radial velocity, but I haven't tried using a neural network to do it.
Okay, and then Chandra wanted to ask one that's hopefully a little quick.
Yeah, I'll make it quick. I was going to ask an elaborate question. But Andrew, great talk first, and also to your co-author. And you didn't intentionally say it this way, but this basically is, you picked up a wide class of problems called radar data quality, which is fundamentally important for ARM. And I'm actually running a group on this radar data quality issue. And it's got huge impact and potential, especially when you start bringing in polarimetry. And so we can talk offline, because I'm running a working group on radar data quality on this, and then with machine learning. So it's got potential.
All right, sounds good.
Thank you.
Okay, and there's one more question in the Q&A that Andrew can answer offline, but we'll go ahead and move on to our next speaker.